Hi, my name is Muyang Liu, a PhD student at the University of Edinburgh, and it's my pleasure to introduce our work to you. The paper I will present is titled A Hierarchical Contraction Scheme for Querying Big Graphs. Nowadays, graphs are widely used in many areas, for example, artificial intelligence and social network analysis. Real-life graphs are often huge these days, which may have trillions of edges. What makes it worse is that graph computations are often costly. For example, consider checking the connectivity of a graph with trillions of edges. This routine application takes more than 300 seconds on a cluster with more than 10,000 processors and requires at least 100 terabyte memory. The cost is more staggering when it comes to applications with higher complexity, like graph-pattern matching. So we are trying to find, can we make graphs small enough to fit into the memory of a single machine? Can we handle multiple query classes and compute exact answers on the same graph? It's about finding a representation of graphs that is generic, lossless, and can be handled with bounded computation resource. On top of that, can we adopt existing query evaluation algorithms to the compact graph representation without the need to redevelop the algorithm starting from the scratch? Plus, what if the graph is constantly changing, and how can we efficiently maintain the representation? The answer is yes to all of these questions, and we will answer them one by one by building a hierarchical graph contraction scheme. A lot of researchers have already studied on this topic, and I will first briefly summarize these works. Firstly, we discuss studies that aim to reduce the size of graphs, such as graph compression and summarization. Graph compression computes query equivalence relations and merges equivalent nodes. Graph summarization generates summaries for nodes or subgraphs. However, graph compression is usually query dependent, and summarization is usually lossy. Then we talk about querying big graphs. Distributed computation systems partition the big graph into fragments and process all fragments in parallel. However, parallel scalability is not guaranteed for all problems. Another approach is querying big graphs with a single machine. By using disks as an extension of memory, single machine systems split the graph into a great number of disjoint intervals and answer queries by accessing the intervals from disk. However, most disk-based systems adopt vertex-centric model, which requires users to recast existing algorithms into the model. As opposed to the prior works, our hierarchical contraction scheme is generic, which means users can run multiple applications simultaneously. And the scheme is also lossless. Users can answer queries with no information loss. At last, the scheme can adopt existing graph algorithms with minor changes instead of redeveloping algorithms. In today's talk, I will first show how we define and build the hierarchical contraction scheme for a large graph. Then I will show how to compute exact answers on the scheme using PageRank as an example. After that, I will talk about how to incrementally maintain the scheme when it comes to graph updates, and finally show the results on real-life datasets. Before we start talking about the actual scheme, let's first review some basic notations. In this work, we assume that the graph is undirected. Each node and edge has a label on it. A graph query is simply a computable function from a graph to another object. The object can be a Boolean value, a graph, or a relation. Now we are ready to define the scheme. A hierarchical contraction scheme is in k levels. Each level is formed by one contracted graph G and four auxiliary functions FC, S, FD, and FR. G is the contracted graph, which is formed by supernodes and superedges. FC is a contraction function such that given a graph G, we can apply FC to deduce a small graph from G by contracting subgraphs into supernodes. FD is a decontraction function that restores each supernode to its contracted subgraph. FR is a special decontraction function to retrieve node lists of supernodes. S is a set of synopses such that for each query class in use, there exists a certain set of synopses which annotate each supernode. By contracting subgraphs level by level, we can easily achieve a compact representation which will fit in the memory on the top level. But how do we ensure that the hierarchical scheme is generic and lossless? Note that FC, FD, FR, and G are all application independent. All queries will share the same. Although synopsis is application dependent, it is query independent. It means that all queries of a certain type use the same use the same synopsis instead of having a synopsis for each individual query. Next, to ensure the scheme is lossless, we rely on both the synopsis and decontraction function. Whenever a query needs to be evaluated, we first check the synopsis, and if it gives enough information, we answer the query without any decontraction. If not, we will decontract the necessary nodes and edges to restore those contracted subgraphs level by level, and then answer the query. In this way, we can ensure no answer is lost or twisted. We contract topological components, which are connected subgraphs with certain topological structures. In this work, we mine the topological structures from each type of real-life graphs and verify them manually. Typically, we use click, star, plus diamond, and butterfly. Let's see the example of a Twitter graph fragment. In this graph, a node can denote a user by U, a tweet by T, and a keyword by K. An edge have different meanings based on their endpoints. For example, an edge between two users means the two users are friends. It's not hard to recognize the components to contract. In this example, we can see a click formed by K1 to K5 on the top left and another click in the middle. There is also a star, a butterfly, and a diamond in the fragment. Furthermore, there are also some singleton nodes such as T1 and T2, which don't belong to any specific structures. Different types of graphs have different dominating regular structures. For example, you may find more clicks in social networks, but almost none in road networks. We identify the order of topological components to contract for different types of graphs G. As for the previous example, which is the social graph, we apply the contraction in the order of click, diamond, and star. The order can ensure that important structures are contracted earlier and preserved. Based on the order, the algorithm to contract a graph works as this. The input is an original graph G, the threshold TP to ensure the contraction ratio between levels of the hierarchy scheme. The buffer size B, which restricts the size of each subgraph loaded into the memory, and the memory limit N. It starts with loading subgraphs from these and contracting topological components on the subgraph, following the predefined order. After this process, nodes left as singletons are mapped to themselves. It contracts graph levels by level until the size of contracted graph on the top level is less than memory limit M. If the contraction ratio between two levels is less than the threshold TP, which means the size of contracted graph is not substantially reduced by contracting topological components only. Then we adopt edge contraction to further reduce the size of the graph until the memory limit is satisfied. Edge contraction contracts arbitrary subgraphs as long as the size of the subgraph is less than buffer size B. The algorithm costs at most OG square time, but since the scheme is generic, we need to contract the graph only once. At last, we deduce the synopsis for the scheme. The synopsis includes information for two aspects, topological information and application information. Topological information is about the topological structure, and the application-dependent synopsis is deduced for certain applications. Then we come to the contraction of the Twitter graph fragment G0. On the first level, topological components are contracted. For example, click on the top left is contracted to S2, and the butterfly on the top right is contracted to S4. Then on the second level, a diamond on the right-hand side is contracted. The edge S3, S1, and the triangle on the top left is contracted by edge contraction since there is no more specific topological structures. At last, we get the contracted graph G2 on the top level. To show how to evaluate a query on the scheme, I briefly introduce how to compute the PageRank query on the hierarchical scheme as an example. PageRank aims to compute PageRank score of all nodes on the graph. The synopsis of PageRank is just the topological synopsis. We use a Boolean value to denote whether a supernode is converged and skip redundant computation on converged nodes. The algorithm is basically the same with the classical PageRank algorithm. The only different part is that if all nodes contracted to a supernode are converged, then we say the supernode is also converged and skip computation over the supernode, including all nodes contracted to the supernode. For now, we settled down the hierarchical contraction in the static setting. That means no updates will occur. But what if the graph regularly changes? That's when we need to incrementally maintain the scheme. It would be too costly to reconstruct the graph from scratch whenever a single node or edge changes. We can measure the complexity of incremental algorithms in terms of the size of the affected area. By affected area, we mean the changes of graphs as the input or the changes to the scheme as the output, and any other nodes and edges that are directly connected to these changes. We say the algorithm is bounded if its complexity is determined by the affected area only, not by the size of the entire graph. A bounded incremental algorithm is often far more efficient than recomputing from scratch, since the updates are often much smaller than the possibly very large graph. We can see that the topological components are fragile. For example, when inserting an edge between two leaves of a star, the star will no longer be a star and its nodes may need to be merged into other topological components. In this paper, we designed the following incremental algorithm for scheme maintenance. There are these 3 steps for each level of the scheme and iterating from bottom level to top level. The first step is to identify the area affected by updates. We first identify updates that won't affect the structure of the contracted graph and directly apply them to the graphs. Secondly, we apply changes to the contracted graph and update the contracted graphs. For each affected supernode, we first recover contracted subgraph and apply updates on the subgraphs and at last contract them again. Now some nodes may become singleton nodes since the topological structure may be decomposed by updates. Hence, in the last step, we collect the singleton nodes in the node set and contract them after applying updates on the current level. We iteratively apply the 3 steps to each level of the hierarchical scheme from bottom level to top level. After all leaves have been processed, we compute the synopsis of affected supernodes only. We say the complexity for incremental synopsis maintenance of applications like PageRank, pattern matching is at most a square of affected area and is a bounded incremental algorithm. We experimentally verified the whole contraction scheme under both static and dynamic settings on a single machine. We select 6 different types of queries and compare with the effective of query evaluation with both memory-based and disk-based systems. We find the following. First, on average, the hierarchical contraction scheme reduces graphs by around 90% to fit in the memory. Secondly, on average, it improves the evaluation of the 6 applications by more than 9 times against both disk-based and memory-based systems. Then compared with memory-based systems, the scheme takes around 3 times less space cost, while the scheme spends 22% more space compared with disk-based systems. The reason is that the scheme stores more information, such as synopsis and contracted graphs in the middle level. At the last, incremental maintenance is on average 4.9 times faster than contracting graphs starting from the scratch, which shows the efficiency of incremental algorithm. At last, we have proposed a hierarchical contraction scheme to make B graphs small enough to fit in the memory as a generic optimization scheme for multiple applications to run on the same graph. We have shown that the scheme is generic and lossless. In addition, existing query evaluation algorithms can be adopted to compute exact answers, mostly without deconstructing topological components. One topic for future work is to explore what topological structures to contract for approximation computation. Another topic is to apply the scheme for graph convolution network, which is the popular machine learning model on graphs. And at last, thanks everyone for your attention and your time.